Okay, so both linear and multiple, they use straight line to best fit the point. But sometimes, okay, best fit may not be a straight line, right? That's what I said. Different algorithm that we have, okay, um, understands or best fits the line with different, um, uh, you know, plots, okay? So when maybe situation where your data points may not lie in straight line, right? So we have a data set here, okay? I'm going to take you to the Chrome 1 second. Okay, we'll go back. This was a multiple linear regression data set. So I have a data here called position and salaries. Okay. So here you have position, level, and salary. Okay. This is a data set. Very simple data set. Okay. Position, level, and salary. So how many features are here? How many features do we have here? No, salary is what we want to predict. Salary is not a feature. Total columns are 3, but salary is a column that we want to predict, right? So salary is not a feature, right? Features are your X independent variable. Salary is a dependent variable, the target variable. Feature versus target. This is target. Feature, target, independent, dependent. Okay, X, Y. The salary is your target variable, and position and level are your features. But now if you see position and level both, they are correlated, isn't it? Level is a numerical representative of position. So what we discussed that when you have two columns which are correlated with each other, then we shouldn't take both. We should take only one. So in this case, okay, we can have only one feature. Okay, so let's take the raw version of it. Okay, we are going to read it. Let's go back to our PyCharm. Okay, and I'm going to replace the link here. Okay, all good. Now X will be here. Okay, from 1 to 2, right? So we are ignoring the first column and we are taking only one column as your X, right? Only one feature. Okay. Okay. Now you can have here Y, and Y is going to be your third column, right? Okay. Now here there is no missing value. There is no categorical value as well. So we don't have to do this one also. Okay. Okay. No need to do backward elimination here. Okay. We can plot the graph and see. Okay. So here we have only one. So we'll draw only one scatter plot. On x-axis, we have something called as position, right? I'm just going and checking. It's position level, sorry. Level is what we are interested. Position is the text value. And Y is salary. Spelling should match, okay? Level and salary. Okay. So we'll see how it looks like. We can divide into training set and test set, or for in this case, let's not even do that. Data set is very small, right? So we will not do that. We'll directly plot and see what happens. Okay. We are going to use, okay. So model building, what we'll do is we will comment all these and we'll come back and uncomment one by one. So from here till here. Okay. This is anyway, this is going to change. So I'm going to, okay. Then testing also. Let me comment it out. Okay. We'll uncomment them one by one. Perfect. Okay. So any error? Why it's showing red here? This is to, okay. I think we've got too many things here. Yeah, now it's fine. Okay, so very simple. We are reading the data, okay, and we commented everything else, and we are just plotting the data, right? So let's see what happens. P1, I'm going to run it. It's reading. Okay, now you see, this is the plot. Okay, on x-axis, we have put level. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, up to 10. And this is the salary, 1 into 10 to the power of 6, right? Lakhs. Now, if you see this data here, this data looks like a parabola shape, right? No, what do you say? No straight line can fit it. You cannot have a straight line which will fit it. So your simple linear multiple, obviously there's no question, right? Your simple linear will fail miserably. With me? Okay. Now, if I take this and if I take it to the paint here, where is paint? I don't have it open. So let me start. Okay. So if you try to draw a line, you can't have a line which can, you know, so it shows there's a positive correlation. Okay. So there's a positive correlation between level and salary. As level increases, salary also increases. But this relationship is not linear, right? Okay. You see first line. Okay. Maybe these points, first and this point is, okay. So sorry. This point and this point probably are near. But these points are away and this point is far away, right? You cannot have a line, okay? Now, let's go and see this, okay? Let's go to our program and let's see what I'm trying to say. So if I try to do, okay, linear regression model, we'll try to do linear regression model and we will see our errors. So I'm going to take okay, I'm going to take entire X and Y, okay, because there is no, I mean, data set is very small, right? Only 10 rows. So I'm going to say X train and, oh, sorry, X and Y. There's no training, right? We are not doing training. So I'll take X and Y. Okay, so linear regression, you can see the coefficient, okay. We will copy and paste it here. Okay, and directly we can, okay, we will do prediction on X only. Okay, so which what I'm trying to do here, I'm trying to calculate training accuracy only, training accuracy. Okay, or what I'll do, because again everywhere I have to change it, right? So instead I will say here, okay, since data set is too small, Let's take entire data for training. Okay, so your X train comma Y train equal to X comma Y. Problem solved, right? So this is regression fit. We'll see what data gives us. Okay, now prediction also will predict with X train only. Okay, here also I have to change all these things, right? Test and train. Train anyway is good. Okay, let me put train test also same thing. X test, Y test. Okay, so it's all X only, X, Y. Okay, so okay, so we are going to run linear regression. We will predict the value. We'll create the data frame with actual and the predicted. Okay, and this will help us to calculate the errors. Okay, and what we can do is we can also draw a plot here, scatter plot with the regression line. Okay, so okay, let's for this case we are not going to do OLS model. Okay, no need to do OLS. I'm going to delete it. Okay. Okay. So we calculated, both will give us same. They should give us same, right? Because we are doing on same data. So it doesn't make sense, but it's a template. So let it be, because, we will use the same template for all the other regression algorithms as well. Okay. Now here, I'm going to say, plotting the data for output. Okay. So here we will say, okay, we will take same plot here. Okay. We'll draw XY axis. Where is XY? Yeah. We'll take same XY. But before we, okay, but before we actually plot, we will add this line, the regression line. So I'm going to say plot, sorry, PLT dot plot. Okay. Here you have X versus Y pred. Okay. We'll draw Y pred. Perfect. You want to put some label, you can put label. PLT dot X label. On X, what do we have? In X, we have on X we have level, right? And PLT dot Y label, we can say salary. Okay, let's run this and see what happens. So we are drawing Y pred, isn't it? So Y pred is based on simple linear. So this is actual data. So can you see this straight line here? Guys, can you see the plot?
Yes, sir. Yes, sir.
Yes. So what you see in the plot here, we have a straight line. This is because of the linear regression. So these 2 points are closer, but see, there is a lot of error here, obviously, right? Okay, so this is what our linear regression is doing. So now if you go back and see the plot, okay, so, okay, see this. Predicted. Actually, is 45,000 for level 0 is predicting minus value. Okay, this is the closest point, 6,000, but see, so off. Okay, again the error is increasing. Probably somewhere here it is very close. But again, here there's a lot of error. So if you see RMSE, okay, RMSE is what? Okay, 1,63,000, too high error. And your R square is 66.9, 0.669, right? The previous cases we have seen R square is 99, 98, right? Here you see it's 0.66, far off. That's why it shows that this is clearly not the best way to implement. Now, when you plot the graph, when you plot this, okay, can you see my paint?
Yes, sir. Yes, sir.
Right? Now, if you look at this, the shape itself, okay, if I can change the color to something bright and size, okay, you can see this is going something like this. This looks more like a parabola kind of thing, okay? So what is parabola? Do you remember the curve of parabola? No, you don't remember, right? So it is getting into, okay, some kind of x square or x cube, quadratic or cubic. Okay, that's all. See, this is straight line where x power is 1. Okay, when you see something which increases slowly and then there's a exponential rise. When you see something like that, this means the power of x is increasing. It could be x square or x cube or x power 4, something like that. So we need to build, okay, we need to build a um, a model that can capture this relationship, isn't it? So let's go back to our program, and we have something called as polynomial. We have something called as polynomial regression analysis. Poly means obviously more than one of power. So we are going to perform our third model, which is polynomial regression analysis. Okay, so how do we call the model and what happens exactly inside this? Okay, so in this case, in polynomial case, okay, your y is something like, okay, constant. I'm going to put constant before only, mx plus c, right? So here c plus you have m1 into x, okay, into, let me put it in this format. So m1 into x plus m2 into x square. So, okay, so we only have x, right? So we are doing x, m1x, m2x square plus m3x cube plus m4x to the power 4, so on. We need to choose. This is the first time we are going to, see how well the model is performing. Okay, so we are going to change this parameter. Now, we have to pass the parameter. So far we directly said linear regression, right? But we have to select here. We have to choose a parameter for this polynomial regression analysis. Should I use 0? If I use 0, then it will be y equal to c. If I say 1, it's going to be c plus mx. If I'm going to say parameter 2, it's going to be till here. If I say parameter 3, it would include x cube also. So we will have to, okay, see how well we are performing our analysis, okay? So if we go back to our, we are on the program only, sorry. Okay, so we have to, okay, now call this the required class to run this model. So I'm going to say from sklearn, okay, from sklearn dot pre-processing, I'm going to call this polynomial features. Import polynomial features, okay? And then the model is called pipeline. So from sklearn dot pipeline import pipeline, okay? So now I need to, okay, change the parameter. I need to, get the parameter, okay? Prepare the parameters, okay? So here I'm going to say parameters equal to, okay? And all these parameters should go as a list here, okay? So first we need to give the set of values, okay? And then you need to tell which model to use, okay? So here I'm going to say, okay, parameter. So I'm going to use that, we are going to use polynomial. See, polynomial with degree 1 is same as your simple linear regression. Okay, if I say degree 1, x is 1, so it is mx plus c only, right? It is same as your. It's only when your degree rises, it goes to 2, 3, that's when your the model changes, right? So I'm going to say polynomial, okay? And here we need to give the features, okay? So polynomial features, okay, here you say degree equal to 2, or let's start with 1, okay? We'll start with 1 and we'll do it for 2 and 3 and so on. Okay. Now, in fact, see, we don't know beforehand, before you start implementing any model, every model will have some parameters. Okay. And you don't know what is the right parameter. You don't know what is the right parameter. Now, when you don't know what is the right parameter, so we need to, do what is called a trial and error. Because we don't know what is, in this case, definitely 1 is not the best answer. We have already seen using simple linear. But should we use 2 or 3 or 4? We're not sure of, right? So we need to, okay, try with all the numbers that we think could be the right choice. Okay, and we will see that. We'll put it in a loop, for loop, and we will, we'll do it. So, okay, so polynomial degree equal to 1. Okay, degree is 1. And here now I need to give, okay, what happened? Okay, so I think, sorry, this is not right. Okay, this would be part of same. So you have first set, okay, polynomial, and second set of value is degree is equal to 2. Now I need to give the model detail. So I'm going to say use, okay, model linear regression only. So I'm going to use linear regression model, but in this case, I'm applying polynomial and with feature equal to 1. Okay, so our parameters are ready. So now call this pipeline. Okay, so I'm going to say pipeline object equal to pipeline. Okay, and you pass your parameters. Ready. So our model is ready. Okay, so what should we do next? Train the model, obviously, right? How do we train the model? Have to train the model and then we have to predict the data, right? So train the model pipe dot fit. Fit is what we used to train, right? Okay, so I'm giving x, comma, y. Okay, so fit is ready. Now we need to predict. So I'm going to say y pred. equal to pipe dot predict, and we'll give X here. So, okay. Now, to evaluate this model, again, we'll go here. We'll draw this graph, and we will calculate bias and, okay, here it's only bias, right? So bias for R square and RMSE. Okay. So, okay, Y-pred, okay. Y-pred. Okay. This is Y-pred equal to regression, right? It's obviously not regression. So here it is pipe, but we don't have to do this one again because we are not doing it differently, right? Or if you want, you can say here. So here it is pipe dot predict. X train is X only. We have already set it, right? So it's going to be trading. Yeah. Plotting the graph. That's it. Okay. So I'm going to comment out this first. Okay. This is not required for now, right? So we will comment out. Okay. Now let's run this and see what happens. Okay, so we are applying pipeline. These two line is enough, right? First, we are passing parameters. Okay, so you see this? This is the graph from linear regression, okay, that we did. Now, this is the graph from polynomial. Do you see any difference? No difference at all, because degree 1 is same as linear regression, okay? No difference at all, right? Okay, now what I'll do, I will put this in a loop, okay? And you tell me, okay, which parameter, okay, which would be better, okay? So what I'll do, I will put a for loop here. For I in range 1, comma, let's do for 10, 1 to 10, okay? And all these will be inside, right? And, okay, here instead of degree equal to 1, I'll put I. So in fact, we're doing from 1 to 9, isn't it? And now after plotting, okay, I'll say PLT dot title. Okay, let's do title. And title, we will have polynomial analysis. Okay. Polynomial analysis, str of I as analysis degree equal to. Okay. So let's run this and see what happens. Okay, so this is our linear regression. Okay, ignore it. Now our loop is starting. See, degree 1. So degree 1, same as the previous one. Now degree 2. You see this degree 2? So it is y equal to c plus m1x plus m2x square. Okay. And when you print the coefficient, in this case, you'll get two coefficient. We are not printing it, but yeah, we can print it coefficient and constant term. You see this line? Tell me yes or no.
Yes.
Yes,
Okay.
sir.
Now let's look at degree 2. What happens when we become degree 2? See? So this is what we are saying, that it is trying to now get into overfitting area. This is what is called overfitting. Okay. If you give too many questions, student will start by hearting. So their performance, see this? 4, 5. See, 5 is so perfect. RMS is, see here, R square is 99.99, almost like 98, right? Your RMSE has going down. Now, if you look here, the values of RMSE here, we started with RMSE of 1,63,000. Okay, so this is same. Okay, linear regression, and this is your polynomial. So 1,63,000. Now it became 82,000. How? It became 38,000. It became 14,000. Now it is 4,000. Okay. Now see, so perfect. It has become 2,000 here. You see it below? Almost like 1 R square. No error at all. You see this? Now if you go down, it is 1,300. Okay. It is 700. It is RMS is almost 0, right? 0.0. See, from 1,60,000 we came to 0.037. Okay. Now, what do you notice here? What did you just see?
The equation is perfect, but should it be perfect?
Okay. That's right. This is called overfitting. Overfitting is what? Your training accuracy is 100%, right? If you remember, okay, and this is what we had discussed, okay. If I go back to Paint, we discussed in variance and bias, okay. Variance is which error? Variance is which error? Variance is test error, right? Your test error will be higher, will start decreasing to a point. Then it goes start going up. Your training error, okay, will be little lower than here, right? Because always this, and this will go on, okay, decreasing. Okay, it will go on like almost close. Okay, so this is what we saw. Okay, that training error is going 0. This is what we saw, but we don't know what is this point. This point is here, or so degree equal to, let's say this is degree equal to 1, degree equal to 2, 3, 4, 5. Okay, so as you go to 9, it is almost 0. Okay, so we know that we have reached into a overfitting. This is your overfitting, right? Okay, and this is underfitting. Underfitting, both training and test error is high. Overfitting is where your training error is very, very low. Okay, accuracy is very high, but your testing is the the by-hearted area where the students started by-hearting questions and answering. The perfect 100% marks, but you don't know whether they've understood or not, right? So when you keep increasing degree, if you keep saying 10, 11, 12, it'll go on closer to this because we are running this on the training data, right? Now, if I do it on test data, then we will come to know, okay, no, there is some error. So what will happen on the training, on the test data, this error will start decreasing to a point. Afterwards, it will start increasing. And when this change happens, that's when you know that, okay, this is the best one. This is where we should stop. Okay, so let's go back again to our model. Okay, and I'm going to uncomment this training and test. Okay, let's uncomment training and test. And here we will take 20%. 10 rows, so 2 we will put as test. Okay, so this is your training test. Okay, train and test. Okay, now we'll come back to our analysis here. Polynomial, we'll focus only on polynomial. Okay, so here, okay, Let's change this. Okay, now we don't have to say x equal to test or train, right? We don't have to say this. We want to know which is the best fit. Okay, which degree is the best answer, right? If you keep on increasing degree equal to 10, you will see islands are being made. Okay, so I can show you this bit. What I'll do, I'll start from 100. Okay, and we'll go to 101. See what happens when I is 100. Uh-oh. You might see any, yeah. Okay, X and Y. Okay, so what I'll do for now, because we have built on this, right? So got stuck 1 second. Yeah, we have built on this, right? So let's run this on this only. Yeah. So this is linear regression. You see this? When we did 100, tick, 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 you know? So this is how you can see with various values of degrees. Okay, now let's do our work. So I'm going to uncomment this, perfect. And I don't want to make X same as train and test. So I'm going to comment this. Okay. Doesn't matter. Okay, so this model I'm going to, we don't need regression analysis for now, right? So I'm going to comment this part. I don't know, it's behaving very slow. Okay, so now this, okay, so this is also inside this one. Okay, now this is also inside this. This is this is all your regression only. Okay, so we'll put them all inside one. Okay, now coming back to our polynomial. Okay, so okay, did I metric also got? This should be up here. Okay, looks good. Okay, so I'm going to perform this on, okay, linear regression also got hidden. So this also we need to put up. This also got commented. Okay, so we have train and test. So first training data on X train Y pred, right? This is our root mean squared of bias. Now we need to create for okay, for test. X test will say variance. Variance is based on validation data or test data. Okay, so X test, so all the X is going to be test. This is, oh, what did I do? Sorry. This is Y, right? So this is Y pred test. I'll put TT here. So Y pred TT, Y pred TT, TT, and this is test. Y test, right? Y is Y test, X is X test. Okay. So, so X training is done on XY, right? This is also wrong. We should do it for X train, right? If we train on X, then what's the point, right? So fit X train and Y train. And now we are saying predict on, I mean, this is anyway not required. because anyway we are predicting again here. So this has no meaning, right? We are doing prediction on train. So this is our train RMSE, and this is our test. Okay. Now, if you want to make it even better, I would suggest, okay, that we go with 30%. Okay, need to have a little more data. So we'll say 30% here. Okay, let's run this. So we created training and test here. So 30% is test, 70% is training. So let's see the model behavior. Okay, so this one you see, this is degree 1. In degree 1, root mean square for bias is 1,62,000. And for, oh, this is variance. This is variance, okay. Let's stop it and run it. We'll get confused if we have same. I've missed to change here. Okay, let's do it again. So see this, okay, degree 1, okay, graph is here, and you see RMSE for bias is 162 and variance is 194, which obviously, right, variance will be higher. But if you look at the difference between them, it is not much, right? 30,000 difference. Okay, in fact, wait, let's do this, okay? Difference between variance and bias. Variance will be higher generally, right? And bias equal to your here I'll say RMSE test equal to okay. Okay, life is not easy. It's not that you run it. That's what running model is very easy. Okay, just 3 line model is done. But evaluation and pre-processing is where your skill will be tested. Okay, so I'm seeing RMSE TT equal to this. Perfect. This is RMSE TT, and similarly I'll calculate RMSE TR. Okay, RMSE TR is MSE into this, and here we will print as TR, and this will be your TT minus TR. Okay, let's run it and see. So degree 1 is coming up. Yeah, so degree 1, okay, like simple linear, and difference you see is 31,900. Now for degree 2, see, for degree 2 it came down, isn't it? Difference came down, 29,800, which is good. So from 31 it came to 29. Degree 3, you see, there is a change here. What happened? The error in variance is lower than the error in test. Okay, so your variance is 0.9. Okay, so what was variance here? Variance here, this is the variance for degree 1, and this is for degree 2. Okay,
Recording in progress.
What happened? Question there? Okay.
No.
Okay, so you see this. So here you have, okay, variance for bias is 42,098 and 90. Okay, and here it was this for degree 2, and for degree 1 you have minus here. Obviously, this is not the best model. Now here, it has started becoming better. 98, 90. It was 94 and minus, actually. R square is minus. So degree 2 seems to be better than, sorry, degree 2, right? Or degree 3? It is degree 3. So degree 3 seems to be better than degree 1 and 2 so far. Okay. Now let's look at degree 4. Degree 4, you see, your variance decreased. From 90, it became 88. You see that? So it is improving up to degree 3. And then for degree 4, this improved. Bias is from 98, it became 99. 99.9 actually, right? From 98, it became 99. Now, if you plot the graph, you get that V-shaped graph for variance and that decreasing graph for bias. For bias, R square is increasing. That means your RMS is decreasing. But here you see, this is where it started changing the position. So we know that degree 4, right? Degree 4 is not the right number, degree 3. So degree 1 and 2, we were in underfitting zone. Degree 3 is the best, okay, the best result this polynomial can give you. Best result polynomial can give you. And degree 4, we are getting into overfitting zone. Now again, if you see here, okay, so here your R square variance has improved, okay, 98. So probably 4 is also, now we have very less data, right? But when you have more data, you need to run it multiple times. Just by running one time doesn't, give you the best result, okay? So probably this is also better. Variance is 98, 98.9, right? Now, degree 6, okay? Variance is getting into, bias is 1 and variance is also 99. Okay, so probably this is also good. So again, it started decreasing here. Difference was just 9 and here it became 3000 difference. Okay, now it should start, it will be higher and higher now. Okay, 3000. Again, 3000. From 9 it went to 3000. So 9, RMS in 9 was the lowest, right? So that is where we say that is the best degree for this exam. Here it again 3000, right? So this is how you can actually see how data changes from underfitting to overfitting. Underfitting is both are low, okay? Both, so okay, so degree 2 and 3 probably was underfitting. Degree 4 probably is the best fit. And then from degree 5 and 6 again, we saw that it is getting into overfitting area. Okay, so bias will always decrease. Only thing is the variance is increasing now. From 99.99 it became 99.8, right? 9.998. It is going up. Error is increasing. Okay. So that's when we say, okay, based on this data, we'll say probably, okay, your, where? 9, this one, no. Difference between them you have to look at. 4000, right? So, where was it? 9,000, okay? So wherever you see there is a least difference between training set and test set. You can try till 20 and you can see how you can draw a Excel. In Excel, you put the column and you put that values there, okay? But again, so this is more from learning perspective. When we do actual examples, we'll have thousands of record and then it will be even more better. Okay, so this is how polynomial works. Any questions so far? Okay.
No, sir.
Next model is called SVR. Support vector machine is the concept. SVR, support vector regression, is the algorithm for regression. Support vector classifier, SVC, is the algorithm for classification. So we are going to now move to non-linear models where the linear model is now behind. We'll get into something different. Okay, and this is again very important model, SVR or SVC, support vector machine. Okay, the concept is support vector machine, and same concept can be used for both regression and classifier. Okay, so we'll see what is SVM and how we can do regression, okay, in this topic. And when we get into classification, we will see how to do classification later. Okay, we'll end it here for today, and we'll see you on